W tym momencie my schodzimy i to będzie
ta bateryjka się kończy.
Okej, Paweł, czy my mamy baterię, żeby...
Ja mogę skoczyć do recepcji i powiedzieć, że...
Tak, tylko przyda też się, żebyśmy to tutaj wpięli, bo Dan akurat używał tego naszego centrowego laptopa.
To jest nasz.
Nie, ten. No ja już skoczę do recepcji, bo jeszcze poproszę ich, żeby włączyć.
Tylko może nie na takie zimne, jak było wczoraj.
Właśnie, pan, tylko nie za zimne.
Okay, I'll try this mic. It seems to work. Let's test it how long it will going to work. Because last time it would turn off after a few minutes.
And these three.
This is more convenient because it's hands-free.
Możemy zaczynać. Paweł, ja przyniesie za chwilę. Czy chcesz poczekać na tego pilota? Dobra, dobra, czyli poczekamy na...
To mogę tylko pokazać myszką. Pokazuję low battery. Zobaczymy.
Masz? Działa? Paweł, nie działa, nie działa.
Jak mogę zmienić to?
A, ty szerujesz stąd. A, no to nie ma prawa. Przepraszam. Teraz będzie działać.
Okay, to jesteśmy gotowi, tak?
Yeah, we're all set up.
All right. Welcome everyone to the second talk of the morning session, and our speaker is Paweł Kularczyk from the Gdańsk University of Technology, and he will speak about a topological method for computational analysis of dynamics.
Thank you. I would like first to thank the organizers for inviting me to this conference and for giving me the opportunity to give this talk. Thank you also for coming. And I'm going to talk about a long-term project that is aimed at a complex method for topological computational analysis of dynamical systems. So the plan of the talk is the following. I will begin with some definitions so that we set up the correct notation. I'm going to explain certain topological invariants that we use in this project. Or in other words, I'm going to take a bunch of definitions and throw them onto you. In the next part, I'm going to explain some technical details and the actual methodology that we use. And eventually, I'm going to show some specific applications of this method. So let's begin with the first part. Just to make sure we all talk about the same things, that we recall the formal definition of a dynamical system. So suppose we have a topological space. This is nowadays called an applied dynamical system, because in general, people tend to take a dynamical system as an action of a group on a space, and this gets very general. We talk about something very practical, and this is, we have a topological space, usually Rn or some part of Rn. Then we have a topological group for measuring time. This will be the integers or the real numbers. And the notion of a dynamical system is the following. We have a specific rule that maps each point in the space and to another point after some specific time. This rule does not change in time. So we have the following conditions. If we move after time 0, then the point, of course, does not move at all. And if we move the point by time t and then the resulting point by time s, then it is equivalent to moving the initial point by the time t plus s. I'm going to talk about two kinds of dynamical systems. When we use the discrete time, then this will be a dynamical system typically induced by a continuous map on the topological space. Well, in the dynamical system, we have the assumption of invertibility because we have the group. Sometimes in practical applications, like dynamics of populations or some biological systems, this map is not invertible. This is not a problem. The theory gets a little more complicated. I mean, the definitions need to be more specific, but essentially everything I'm going to talk about today works in such a setting also. And in fact, some of the examples I'm going to show correspond to semi-dynamical systems where the map is not invertible. Another class of dynamical systems that is very important are continuous time dynamical systems. These are usually flows that are induced by autonomous differential equations, and the trajectories or those solutions to the ODE corresponds to the motion in the dynamical system. So a system of ODEs introduces a dynamical system. So some assumptions are necessary, for example, that the trajectories don't escape to the infinity in finite time and things like that. But in the computations, I'm going to show if any trajectory escapes a certain bounded region, we just don't care about it. So we can assume we have a continuous time dynamical system, at least in the region where the dynamics is of our interest. So in general, a dynamical system might look like this. So there are some trajectories. There is a hyperbolic fixed point. There is a bunch of periodic orbits around another fixed point. There is also another periodic orbit that is repelling. There are some fixed points. In general, the structures we are interested in are invariant sets. We say that a set is invariant if it does not change upon the dynamics. For example, if we have a periodic trajectory, the points move on the trajectory with time, but the trajectory itself as a set does not change. If we take some larger set, then we can define its invariant part as the largest invariant set that is contained in that set, the largest in terms of inclusion. For example, inside this gray disk, its invariant part is just the fixed part, because any other trajectory escapes from this disk either in forward or in backward time. We say that N is an isolated neighborhood if it is compact and its invariant part is contained in its interior. So we would like to get some sort of isolation for those invariant sets, so that we have some safety margin when we do numerical computations. So we must take into account some round of errors, some numerical errors, and this is why we need to have this isolated, to have this invariant set in the interior of this neighborhood. For example, and here we can define what kind of invariant set is isolated. An invariant set is isolated if it has an isolating neighborhood. That is, it is the invariant part of some isolating neighborhood. For example, this fixed point is an isolated invariant set. But if you look at this fixed point, it is not isolated, because no matter how small neighborhood you have, there will always be some extra periodic trajectories included in this neighborhood. However, if you take this large disk, shown in gray, then you see that some trajectories that are close to this yellow disk run away from it. That's why this will be an isolating neighborhood. So now we would like to split the dynamics into recurrent parts, which will consist of these isolated invariant sets, and the remaining of the space will be sort of simple dynamics that runs from one set to another. Specifically, I'm thinking about gradient flow. So suppose we have a surface in R3, and everything moves, all the points move downwards with the gradient. And in this situation, well, in the generic position, we have a finite number of critical points, and all the other trajectories flow from one critical point to another. So these are sort of connections. Now, suppose we have a finite number of these critical points, and we can depict this dynamics, this gradient dynamics, in a schematic way by means of a directed graph. Each node of the graph corresponds to one critical point. The information that we put in the node is the consecutive number 0, 1, 2, 3, 4, and 5. I start numbering points from 0. In mathematics, people start numbering from 1, which is neat. These are the natural numbers. But in computer science, the natural numbers begin with 0. So let's do this computer science way. And then I put the information about the type of stability of each critical point, which is here the dimension of the unstable manifold, and this is called the Morse index. For a repeller, the dimension of the unstable manifold is 2, so I put the index 2 here. For a saddle point, there's only one repelling direction, so the dimension of the unstable manifold is 1, so the index is 1 here. And for an attractor, the index is 0. We would like to get the same kind of description of a general dynamical system, not necessarily a gradient dynamical system. But here the problem is that we might have more sophisticated invariant sets, not just fixed points, but also periodic orbits or some invariant disks, or even some more complicated invariant sets like topological horseshoes and things like that. Yes?
Can I ask a question about the period system?
Sure.
Can you make this image simpler by adding the small condition, the small transversality condition, that you don't have any gradient lines within the critical point with the same index?
Well, I don't know. It could be the fact, but we are not interested in that. We are interested in capturing all the critical points.
But it does the same, but except the fact that you don't have flow lines within the critical points with the same index. If you add that assumption,
yes, but we want to know what kind of transitions are possible between the critical points. This is the key here. So we don't want to make this any simpler than that. It is necessary to reduce the global information about the dynamical system, but not too much, so that we still retain the information that is interesting. So here, on purpose, I keep the information about the possible trajectories between those saddle points. And in fact, I didn't plot the connection between this repeller and this attractor, because then we would get a lot of arrows in the graph. Let's think about this graph as a transitive reduction. So any path in the graph corresponds to a possible trajectory in the dynamical system.
And all of gradient.
Yes, so this is a gradient dynamical system. And this situation can be generalized to a general dynamical system where we also have some other invariant sets, not just critical points. And this is called a Morse decomposition. It was introduced by Conley in the 70s. A Morse decomposition is a finite collection of disjoint isolated invariant sets, such that we have a partial order on these sets. And the partial order is defined by the dynamics. In other words, there could be trajectories joining different isolated invariant sets, but we don't allow to have loops in these connections. If we squeeze these isolated invariant sets into nodes of a graph, we can depict this Morse decompositions by means of a directed graph again, and we can move those nodes up and down to mimic the gradient situation. And because of this assumption on the partial ordering, we don't have loops in this graph. And this is the kind of description of dynamics that we are looking for, and we would like to have this computed automatically. So we give a dynamical system, run the computations, and we get the graph. And well, okay, so this is the information about the dynamics outside the isolated invariant set, because everything that was in the isolated invariant set was just squeezed to a single point. We would like to also have some information, at least about the stability type of those isolated invariant sets, just like we had the Morse index. And a generalization of the Morse index is the Conley index that was introduced by Conley in the 70s, and he initially called this Morse index, but now we call it Conley index. Let me explain in somewhat more details this topological invariant of dynamics. Suppose we have a saddle fixed point like this, so the trajectories on one direction approach this point, all the other directions, the trajectories miss this point, or go outside or leave this vicinity. And the definition of the Conley index is based on the notion of an index pair. The index pair, like an example here, consists of two sets. The larger set, this is the union of the blue and red in this picture, it's called P1, and the smaller set is usually denoted P2 or P0 in some cases. And this subset captures the part of the larger set through which the trajectories leave the isolated neighborhood that is inside. So we have the following three conditions. Let me begin with the third one, because this is probably the most tricky one. This blue part inside must be an isolating neighborhood, so that the invariant part is contained in its interior. There is no invariant set that touches the boundary of this blue set. And then we have these two conditions. I'm not going to read the formulas, I'm going to explain them or using the picture. So first of all, if there is a point in this blue part, and after some time we know that it is outside, it leaves this isolating neighborhood, then it must go through P2. And this is the first condition, saying that its trajectory is inside P1, and at some point we get to this exit set. The second condition says that if there is a point in the exit set, that then it cannot get back into the isolated neighborhood directly, it must either remain in this exit set or leave this entire index pair. Afterwards, it can, of course, come back, but it cannot come back directly from the exit set. This is why the notion of the exit set is so intuitive. This is the set through which the points exit, and the points that are there really exit the set. Well, in some, it may turn out that inside this exit set there is still some invariant set, but we don't worry about this. The purpose of the exit set is to capture how the points exit this isolating neighborhood. There are certain theorems. There is a big theory that justifies the correctness of this definition. In particular, if we define the Conley index, then this is the homology, the relative homology of this index pair. And there are theorems that says that every isolated invariant set has some index pair. If we take two different index pairs for the semi-isolated invariant set, then the Conley index will be equivalent or the same, isomorphic. And the most useful property is that if the Conley index of some index pair is non-trivial, then this means that there exists a non-empty invariant set inside this isolating neighborhood. And this is something that is very important from the numerical point of view. We can construct an index pair and compute its Conley index, and then we have a computer-assisted proof that the invariant part is non-empty, which might not be that easy to prove by using some other means. So I'm going to use this feature a lot. Let me show a few popular Conley indices that appear in dynamical system often. For example, we could have some attractors like fixed points, periodic orbits. We could have some hyperbolic sets, fixed points, periodic orbits again. There are also some trivial indices that appear near bifurcations, where we cannot prove that the dynamics goes through some set. So it appears that the invariant part might be non-empty. However, the Conley index is trivial, which means that we cannot prove that it is really non-empty, and it could be an empty in fact. If we have a set of fixed point, that's just like in the picture before, then let's see what the Conley index looks like. We take the quotient space of this large set P1, and the other part of the pair is P2, and we take so it corresponds to topologically squeezing the exit set to a single point. We take a homotopy equivalent space, which will be just the circle with this specific point that originates from the exit set. And the relative homology means that we don't count this connected component to which the point P belongs. So the homology is 0 in terms of counting connected components, Z at the first position, which corresponds to this loop, and then zeros elsewhere. And this kind of quotient space is called sigma 1. This is the very prominent topological space that corresponds to a hyperbolic fixed point with one directional instability. In higher dimensions, if the dimension of the unstable manifold is 1, the picture looks precisely the same. Now, if there is an attracting fixed point, here I'm putting this for flows, then an isolating neighborhood could be this blue disk. There are no trajectories leaving this neighborhood in forward time, so the exit set is empty. This is a good index pair. And now we take the quotient space, we divide by the empty set, no division by 0. Okay, so instead of dividing by 0, we add an artificial extra point to the space, which is denoted by the asterisk, and we take this asterisk as this extra point to which the exit set that did not exist was squeezed. So the homology of this, the relative homology of the space is the Z. We have just one connected component, no loop. And this is a typical situation when we have an attractor. We just get some number of connected components that correspond to the number of connected components of the isolated neighborhood, and then there is nothing more. Well, except for the structure of this set. If we have a repelling fixed point, then an index pair might look like this. We have a disk, and the exit set is the circle around the disk. We take the quotient space, and this looks like the sphere with this extra point to which the exit set was squeezed. So this is one connected component, but we don't count the connected component to which the exit set was squeezed. And the homology is 0, 0, and Z at the third position, or for dimension 2 homology. Let's see two more situations. If we have an attracting periodic trajectory, then P1 could be this like a belt around this trajectory. All the trajectories enter this neighborhood in forward time, so no trajectories exit. The exit set is empty. Again, we have the division by 0 error, so we have this extra point, and we get the circle and this extra point that doesn't count for homology. So the homology is Z and Z. If we have a repelling, an unstable periodic trajectory with one dimension of instability, then the exit set could be something like the one that's was red here. So in relative homology, we get no connected component because the only connected component contains this one P, and then we have sort of the wedge of this circle and the sphere. Let me take a moment to see why this works. If we squeeze this disk in the middle to a single point, then we squeeze the outer circle to another point. We connect these points, so we get the sphere with the extra string inside, or we can take the string outside. Okay, so these are some typical Conley indices that we see in actual dynamical systems. Now, we can also compute the same invariant, the Conley index for maps, except it gets slightly more technical. Suppose we have this rectangle, the box, that is stretched in one direction and squeezed in another direction by the map. So its image might look like this. This is the green set. Again, we have essentially the same conditions for the index pair, except now they are formulated in terms of a map, not a flow. So they look much simpler. An index pair might look like this. So we have the blue part should be an isolating neighborhood. The red part is the exit set, and we have the condition saying that the image of the blue part does not exit. Well, it's contained in the union of the blue and red. The image of the red part does not intersect the blue part, so it might look like the green, and this isolation condition. And this generalization was made by Andrzej Szymczak in the 90s, and there were some other also equivalent definitions for some specific cases by Mrozek, and some other mathematicians were involved. Nevertheless, these are the conditions for the index pair. And in addition to the relative homology of the index pair, we also need to consider the map induced on this index pair. Thanks to the conditions for the index pair with the excision property, which essentially means, go back on slide, that the image of the green part does not touch the blue set. So this is this extra condition, and in this way, excuse me, the image of the red part, which is marked in green, does not touch the blue part. It sometimes happens in actual computation, so we do another trick, but I'm not going to get into the details. And then we can talk about the map induced on the index pair. So we get this mapping of the index pair forward by one step, And then we can squeeze the green part back to the red set, to the exit set, so that we get an endomorphism. I'm denoting it here into homology, but in the finite setting, I'm going to do the computations. Homology and homology is essentially equivalent. And this definition was given by Marian Rozek. He found out that in addition to considering the index map, you also need to do some quotient, what he called the rel functor. Essentially, it means that you need to take the quotient of this map by the generalized kernel, because there might be some non-trivial homology that is mapped by the map into trivial elements in homology, and you want to get rid of them. You only want to keep the part that becomes that gets invariant under iterations of the map. Okay, so this is just brief information about this fact. The important thing is that in order to compute the Conley index, it is not enough to compute relative homology of the index pair. We also need to be able to compute the map-induced homology, which, from the computational point of view, is a pain in the, or an expensive thing. Okay. Let's have a look at some popular Conley indices, like we have fixed points, periodic orbits. Now the map can either preserve the orientation or not preserve the orientation. We have different cases. For example, if we have an attracting fixed point, I'm plotting like a continuous time dynamical system, but the dynamics is that the points are jumping. So if we have the green point here, its next iterate will be closer to the fixed point, then it will enter the isolating neighborhood, and with each iterate it will get closer. If we have a map that is a time key map for some flow, so this is translation in some flow by some fixed time, then the index map will be the identity. And this is the theorem. So in this example, there's no wonder that we get the identity. The homology, relative homology of the index pair is Z, because we have one connected component. This one doesn't count, and the map maps this connected component to itself. So the index map is the identity. The generator number one in homology is mapped to generator number one to itself. Now, if we have saddle point, then actually we can have two different cases. If this is a map that comes from the flow, then it will preserve the orientation, of course, and we get also the identity as the map in homology. On the other hand, if we have a map that reverses the orientation, so you can think of this rectangle being squeezed in one direction, actually stretched in one direction, squeezed in another, and then flipped the other way. So this part of the exit set is mapped to this little part of the exit set. This part of the exit set is mapped to this part. And if a point like the green dots is approaching the fixed point in the middle along this line, then everything goes like very nice. But if there is a point that is leaving this neighborhood, with each iterate, it gets mapped to the other side of this line. So we have sort of jumping back and forth. And this jumping or this reflection in the space is mapped in, is reflected in the map itself. So the homology of the index pair is the same as in the continuous case, but the map maps this generator into the negative generator. And here, short remark, for computational homology, people often take the coefficients in Z2 for the computations to be faster, the representations to be the single bit representations much quicker. In that case, we would lose this information about the orientation reversing. That's why I tried computing homology over Z. Well, in fact, computing over some finite field might also work. Like Z5, you would see that the generator G1 will be mapped to 4 times G1, which clearly suggests there is the orientation switch. Okay, now there could be some periodic orbits, like a period 2, and then we have 2 connected components for an isolating neighborhood. G1 is mapped to G2 and G2 is mapped to G1. The matrix of the mapping homology is like this. Since these isolated neighborhoods could have complicated structure, there could be some spurious spurious components. We get some sophisticated homology, which nevertheless is mapped in a couple of iterations to 0. It is neat to compute the eigenvalues of this map in homology. To have another, it's a weaker invariant, but it is independent of the computation of the complications of this map. We get straight to the Leray function. If we have a period 3 orbit, for example, then we get a matrix like that, and the eigenvalues are the roots of the unity. And we get this mapping of homology generators one into another. There could be some minus appearing in pairs here, depending on how the generators of homology were chosen by the software. Okay, so this was sort of a lengthy introduction. Now let's get down to the actual algorithms and computations. And it's high time that I eventually define the purpose of the method formally. So as an input, we take a parameter of a family of semi-dynamical systems, which has some parameters. Like this could be a biological system, which has 5 different parameters. And what we need to know about this system is first a formula for it, or at least some computational method to compute images of points and boxes. We have some bounded rectangular region in Rn. This is the phase space, some section of the phase space. We want to have it bounded because we want to know the computations using the computer, so we don't want any infinite numbers involved here. We have a bounded interval for each range for each parameter. So if you have n parameters, we have a rectangular box that contains all the possible parameters, and the output that we would like to get is a database of dynamics that appears in the system. We would like to have this dynamics expressed in terms of Conley Morse graphs, this kind of graphs that show the isolated invariant sets, the possible connections between them, and the Conley indices of each of the sets. And from this database, we would like to be able to ask some questions like get existence of invariant sets of certain types. We can ask for attractors, for periodic sets. We would like to be able to identify parameters or collections of parameters for which the dynamics looks the same, and also detect possible bifurcations. This is where the dynamics doesn't look the same. And if we look at specific changes in the dynamics, we could infer the fact that some bifurcations occur. We started this, well, this project was started earlier. We used even certain software and algorithms that I developed in my PhD thesis in 2001. Our major paper is 2009, and then there were a few other papers with some generalizations and additional applications. Let me now say some comparison to the classical methods of analysis of dynamical systems. The classical methods are typically either analytical methods where you analyze the equations. People usually can solve the equations for equilibria, compute their stability by linearization, and finding periodic orbits is a little tricky with this. there are a lot of numerical simulations that can be done to dynamical systems, but then you essentially get stable sets. You iterate some trajectory in the simplest setting. You just iterate using the Runge-Kutta method or some other numerical method, and then the trajectories that you start from different points in the space stabilize at some points, and then you get only attractors. This method, well, any kind of qualitative analysis of dynamical systems requires tremendous reduction of information. You don't want to have a database of all the trajectories in the space, because it will be difficult to search through. We want to get some limited, small kind of information that still retains the important parts about the dynamics. Like the Conley graphs shows the major recurrent, in fact, it shows all the recurrent dynamics in the system and possible connections between these sets. So here we can find invariant sets that are not necessarily stationary points. So we can get periodic orbits or some more sophisticated invariant sets like invariant tori or periodic solutions. We also can get unstable solutions for the set, for the dynamics, because in this method we compute all the isolated invariant sets. And we also get information about connecting orbits between them. Now, I'm going to show, in fact, the computations are run and the algorithms work for dynamical systems with discrete time, but there are theorems that say that if we take a time map, then essentially we get precisely the correct information for the continuous time dynamical system if we analyze the time map. In particular, isolated invariant sets that we compute are for the time map are isolated invariant for the flow. The Conley indices are the same. Let me just briefly skip this. And the Morse decomposition that we obtain is also valid for the flow. And now the computation that we do for the time map, the idea is to discretize the phase space. We just take a rectangular grid and we do computations for each cube or hypercube or for each box of points in the phase space. So we do the computations collectively, not to iterate individual points, we iterate individual sets. And we use the CAPD software that is developed in Krakow. This software contains some interval arithmetic, rigorous numerical integration of ODEs that is done with in a very efficient and effective way by taking sets with different coordinate systems, like parallel pipets can be iterated further to minimize some overestimates. So suppose the image of a box looks like this dark gray set. We enclose this image in a product of intervals. This is a rigorous computation. And then we cover this image by boxes. So we say that we have a multi-valued map that maps each box into a collection of boxes. And this is a representation of a continuous map. And we represent this map in terms of a directed graph. Each node of the graph corresponds to a box in the phase space, and each edge in the graph or directed arrow corresponds to the mapping. It turns out that this simple representation can be used to obtain all the information we need. So we run graph algorithms. In fact, we find strongly connected path components of the graph. This is a computer science part of this project. A connected path, a path component is a collection of nodes, of vertices in the graph, so that from each node there is a path in the graph to another node and back with another path to this one. So all these nodes are connected by paths going back and forth in the graph. And it turns out that once we have computed these components, we actually computed isolating neighborhoods for the dynamical system, because this was a representation of the map. And even better, we already have index pairs for the map, because if we take a combinatorial Morse set or this component, then we just take the forward image for the exit set. For example, so the definition of an index pair in the context of in this combinatorial context of cubical boxes could be that well, we actually have two conditions only. The image of the blue part is contained in blue and red, so it could look like the green set, and the image of the exit set could be like denoted in red here, does not intersect the blue. It can touch it, but it does not intersect in terms of cubes. And we don't have the condition about the isolation because we got it for free, thanks to the fact that it was an isolating, it was a representation of this continuous path. Now the actual computations of the Conley index, well, the relative homology of the index pair is not so tough, but computing the map is quite time consuming. There were several papers on which the algorithms are based, and to compute the eigenvalues, we just use the LAPACK linear algebra package, the standard C++ software. Now, it's not working. There is some very interesting software problem. Okay. Yes, now it works. Thank you. Okay, so the last piece of this puzzle is once we have computed Conley Morse graphs for all the parameter boxes, because here we also divide these parameters, this huge box of parameters, into smaller boxes. We do the computations in interval arithmetic. So instead of computing the dynamical system and integrating this in a rigorous way for an individual value of parameter, we just do the computations for intervals of parameters. And we still get valid outer bounds. So suppose we have some computations for adjacent parameter boxes. Now we compare the Conley Morse graphs. If we cannot find a one-to-one correspondence between the isolating neighborhoods, then we conclude that, well, it can be mathematically proven that there is some sort of continuation between these systems. In this way, we get an equivalence relation on the parameter boxes. It would be ideal to do the computations for large parameter intervals in some regions of the phase space or of space where the computations are not so demanding, and do some refinements in some more demanding parameters. We don't do that yet. However, we do a gradual subdivision in the phase space when we compute the Morse decomposition. We refine the initially very coarse grid, and then we compute the invariant part, and we restrict our further computations just to the invariant part. Because by doing these computations, we prove numerically, so this is a mathematical computer-assisted proof, that all the trajectories from outside this invariant part actually leave this part of phase space in forward or backward time. So we are not interested in these. And here's an example of some computation where with gradual refinements already after 4 steps, most of the phase space was thrown away. And this tremendously reduces the amount of computations that we actually do. Now, finally, the results. What we would like to obtain is first an example system that we analyzed is a Leslie population model. It's a D-dimensional dynamical system. This is a map, so it's a discrete time dynamical system with some nonlinearity, and our 2D parameters. What people were doing in the literature is fixing everything except for one parameter, and for example, computing bifurcation diagrams. What we would like to do is not fixing all the parameters, but just fixing some, and analyzing the global dynamics with respect to all the other parameters vary in time. And the images that we obtain is sometimes then we call this continuation diagram, and this is the box of the parameters divided into classes of equivalent parameters. The results of these computations can be found on this web page. I put the address here, and also this web page contains all the software that we use for doing the computations and for visualizing the results. In fact, just before the conference, there was a workshop on numerical methods, on computational mathematical methods, where I was doing a live demo of downloading the software, compiling, running computations, and after a few minor changes in the code, it worked. So let me show what we can get from this kind of diagram. For example, we can look at these classes of parameters and see how they are connected. And here, I don't know how informative this kind of diagram is, but anyway, you can get all the adjacent classes, connections, and possible bifurcations are just paths in this diagram. If you look at different parameter boxes, for example, if you follow this way, you can see some bifurcations. Like we have a period 2 attractor, which we can recognize by the Conley index, but this is an attractor. There is a saddle. I mean, this is an isolating neighborhood that looks like an isolating neighborhood of a saddle fixed point. There is no proof that there exists a saddle fixed point inside. If you want to prove this, then you must use some numerical methods that involve the derivatives. This is a topological method. So you get topological properties, and the results are valid for all the classes of maps, continuous maps that for which this representation, this box-to-box map is valid. Then we get some bifurcations, like undoing the period W bifurcation. There is a period 3 orbit that its Conley index is trivial, but after you move a little bit with the parameters, it splits into a fixed period 3 attractor and a period 3 saddle. So this is a saddle node bifurcation, except at period 3. Well, by the way, this situation is quite interesting because you've got 2 attractors, and this contradicts the commonly held belief among some biologists who say that it doesn't matter what the initial conditions of the biological system are, the situation will stabilize eventually. Now we have computer-assisted proof of the fact that there could be 2 different kinds of stabilization. And then some more bifurcations. In some cases, the isolated neighborhood is quite large, and in this method, we don't get any insight into the dynamics of that is inside this isolating neighborhood. This is an ongoing project that we do at Gdańsk University of Technology with Justyna and Gradual to get some computational graph-based methods for the analysis of the dynamics inside these isolating neighborhoods. Now, what the best we can do is to compute the Conley index and to get some information from the outside to see what might be inside. Since my time is almost over, let me just show one more application. So there were some applications with physicists. There was a 3-dimensional system of ODEs that models plasma, and it is important to know the phase transitions in plasma in order to eventually build the hydrogen power plant, but it will take some time. And using this method, we found some regions of parameters where there are some limit cycles, and we checked this from the topological point of view that these are cycles, not just large isolated neighborhoods. And something that is important nowadays, we also apply this to some model in epidemiology. This is a collaboration with some co-authors in Hungary. There was a 4-dimensional ODE, pretty realistic for modeling 2 cities connected by transportation. And there were a lot of different parameters included in the model, like the vaccination rate, the degree of susceptibility reduction, and things like that. And the interesting thing that we found was that with even small changes in the parameters, the dynamics can vary drastically. And in some cases, that there are up to 4 different attractors, which confirms, that sort of justifies why those predictions for the development of the epidemic were so wrong at times. Well, this is because the system itself the models already are very sophisticated, and there are a lot of uncertainties in the models. Eventually, let me point out the fact that this is sort of an interdisciplinary research. As you saw, it involves dynamical systems, computational algebraic topology, so some algorithms, rigorous numerics, graph algorithms, and scientific computing, because I didn't say how costly these computations were, but they took several hours on the computer cluster. It's not that computing so many Conley indices can be done on it. And this is in fact also a cross-disciplinary research. You get some potential applications in population biology, theoretical physics, epidemiology, and wherever you use dynamical systems for modeling. That's all I wanted to say. Thank you for your attention.
Thank you very much. Do you have questions or comments?
Yeah, so my background is visualization, and we are using dynamical systems more for flow analysis. Simplified, but one of the basic assumptions is that your system is not time dependent,
Right.
which is often not the case for flows.
That's right.
What do you think we can do to model time for which is linear? Or would you need a completely different definition of these invariant sets and these?
Well, I think that with time dependence, this breaks everything here. You get sort of an infinite dimensional system if you want to model this correctly. So unfortunately, this doesn't work. As far as I'm aware, the modifications would be much deeper than I can handle.
And you didn't just put the time as a parameter?
Well, if you take the time as the parameter, then you get a fixed dynamical system, and then you can see how the dynamical system itself varies when you vary this parameter. But I think you will get a different kind of results. I'm not sure how this would relate to the fact that the time can change while the dynamic or the parameter can change while we continue with the dynamics. Here, using the graph algorithm, you look at this entire phase space and the entire range of time at the same time, at one fell swoop. And if the system varies in time, then the graph would change in time also. And so this would require a completely different approach, I think.
Yeah.
So, I don't know if you can hear me.
Yeah, I can hear you.
So I'm curious, you can scale up the parameter computation to higher dimensions than two. Because you, on these pictures, you have like
Sure.
parameters. So can you do like a three-dimensional graph maybe? And also
Yes, the computational complexity increases exponentially with the dimension, but the theory and the software in principle can work in any finite dimension in the phase space and in the parameter space. So for example, in this model, we did computations in 4-dimensional phase space, and this was for an ODE, so it involved integration, a rigorous integration, but CAPD library performs just amazing in this case. And for the parameters, you can do the computations for 3 parameters varying in some ranges. But then there's some problem with visualization of this. I think I can show we actually did computations of the Leslie model for 3 parameters varying. Let me try and launch the web page. Here I've got the link. Let me go here. Okay, you can't see this again. I need some technical help.
Share the browser.
Okay, so this is the diagram. It is interactive, so you can click each parameter and see the Conley graph and the phase space. You can easily see the phase space because it's 2-dimensional. For high dimensions, the purpose of the software is that you don't need to visualize this to see the dynamics, but instead compute the invariants and to infer the dynamical properties from the graphs. And here is the illustration of the 3-dimensional computations. So we computed 40 layers or 50 by 50 parameters. And then when you move in the 3-dimensional space of parameters, then some regions of parameters that were separate in the 2-dimensional picture now turn out to be joined in the higher dimensions. So here you can see, for example, the black region of parameters. It is painted in black. For some, in some slices, it consists of a few connected components, but then you see through the animation that these components actually merge at different points. So this shows that the dynamics for these parameter boxes are equivalent. It is also possible to visualize the parameter sets. I don't know how well you can see the structure. So this is a visualization of the set of parameters that was painted in black. It consists of 80,000 boxes, and a sample Conley graph and phase space look like this. You can do the same for another parameter box. For example, the blue region has this kind of structure in R3. Okay.
So how long did it take to output the information?
So it was, the computations were done a couple of years ago, and it took maybe like 100 hours of 20 CPUs working together. Well, if you have access to a good computer cluster, like I have in Gdańsk, there's a task computer cluster, which is on the list of the fastest 500 computers in the world. So it's only a matter of how long I want to wait to get the nodes assigned and then to have the results completed. A little problem, though, is with the memory, because even if those computer clusters, the memory is typically bound by like 2 gigs or 4 gigs per process. And each process computes the Conley index. The computation of the index map is the most time-consuming and memory-consuming. So this is the main technical limitation of this method, which also shows that there's still need for the improvements in this field.
Okay, any other questions? Not, let's thank Pavel again. And we now have a coffee break until 11:30. Or 40.
Let's be realistic.
Cool.
Okay, we have two announcements, right?
Yeah, on screen. Announcement number 1 is tomorrow we have an excursion to Poznan.
Thank you. Tomorrow we have excursion to Poznań. Well, there are a bit more. If we consider that everybody is going, we should have 2 buses.